So, good afternoon, everyone. Welcome to our computer science seminar. Today, our speaker is Dr. Shashi Shikha. Dr. Shikha has been working as a professor at the University of Minnesota since he received his doctorate from UC Berkeley. So he's a leading scholar of spatial computing and geographic information systems. Dr. Shikha has served as an editor-in-chief for several journals and as a chair for several international conferences. So one conference is called ACM Special Interest Group on Spatial Information, which actually is happening right now at the Marriott Waterfront Hotel in Seattle. Dr. Shikha has received a lot of recognitions from the university level, such as Midnight Distinguished Professor of Teaching, to the national level, such as IEEE Fellow. So, in the end, I want to share an interesting fact with you. That fact is also the reason why I'm here to introduce Dr. Shikha. When I was a PhD student, one of my PhD dissertation committees is Dr. Jiang Zhe, and actually, Dr. Shikha is Dr. Jiang's advisor. So from this perspective, Dr. Shikha is my academic grandfather. Now, please welcome Dr. Shikha.
Thank you so much for a very warm introduction, and also Pan Wang Wei is a close collaborator. She was the local organizer for the conference. And earlier also when she organized some events in UAE universities where we work. So today I just wanted to share a little bit on what I call spatial data science or GeoAI. And I'll kind of briefly give you the background of what this topic is. It's likely that many of you are using systems which relate to this. For example, Google Maps or Apple Maps. Even take Uber, Lyft, those kinds of things. Okay. During pandemic with food delivery, it was very essential, right? Everything. But underneath these systems, there are some very interesting computing challenges and issues. And oftentimes the generic solution, one size fits all, that you may learn in data science or AI, they are not always very effective with this data. So that's why we have developed sort of new techniques and so on. But I will first start with a historical context, and also for me to just understand the audience a little bit. If you don't mind, just please raise your hand if you're faculty members here. Okay, great. Also computer science majors, either faculty members, students here. Okay, good. So folks who haven't raised their hand, could you just tell me quickly of your disciplinary background? So outside computer science, people in electrical engineering here, or geography, a few civil engineering there. Okay, great. So again, this talk is meant for a broad audience. So but if you see vocabulary or terms, if I'm using it in a way that doesn't make sense, just raise your hand and stop. We'll discuss. All right, and it kind of gives you the color of my glasses. So I have been in this area for almost 30 years. And these are some of the books. And this is sort of one of the most recent ones, which is for a very broad audience, not a very technical book. But this has a little more technical information and so on. Also acknowledgement, as I have been fortunate to have support from many federal agencies, and we are going to skip that. So let's actually go to a historic story, because that can give us a sense of what spatial data science is, what are its strengths, and what is the scope. So this is the story of 1854 cholera. And back then, so this is very much like the pandemic we just went through, right? Last 2.5 years. And as you know, beginning of the pandemic, the scientific knowledge was very immature, right? And over the months, we learned a lot of things about pandemic. So if you go back 1854, it was the same situation with cholera, with plague and many other things. So in case of cholera, the dominant theory was what's called Maizama theory, which said it spreads through air, bad air. And people will put beaks full of spices and so on to protect themselves. But then the major change that happened was John Snow made a map. He went door to door to survey the deaths in Colorado. How many of us have seen this map before? Few of us, great. So public health, in geography, visualization, many people share that. But this map showed something very interesting. So here the little dots are the deaths, that you see here. And we noticed that deaths were concentrated in one neighborhood, Soho neighborhood of London. And the center of that neighborhood was a water pump, which is this big square. You see this Broad Street water pump. So looking at this map, spatially, all of us have spatial intuition because we have all lived on the surface of the earth, right? So when you see this, what do you hypothesize? This water pump has something to do with it, right? And he went and he talked to city officials, but the science was not with him. So city officials were skeptic, but after 2, 3, 4 trips, things were getting worse. So they took a chance and they said, okay, we'll do an experiment to test your hypothesis or your conjecture. So let's take this pump off. This was a private pump, so it took some guts for the city officials to do that, right? And it started subsiding the cholera. And what it essentially did was create a new hypothesis. Okay? So you can't call it science, right? You can say, well, this is a conjecture or hypothesis that maybe cholera has something to do with the water. Okay? And back then, germ theory was very new and fledgling, not enough support, but this gave germ theories more legs. And people started pointing a microscope about 20 years later with controlled experiments, with all the other things. Germ theory got much more scientific evidence and legs. Right? And now you, of course, know germ theory has major impact on our society. Right? We wash hands with soap, which was not the practice before. The cleaning water and all that is separated in the city and so on. So this tells you both the strengths and limits of spatial data science. It can generate the hypothesis. Okay, so when we look at spatial data, you can see many types of patterns. Right? Nowadays, we talk about spatiotemporal patterns of life, and many people look at that, and I will show you many more patterns. So it can generate that, but we cannot just stop here. If you want to take it to the level of science, you still have to go through rest of scientific methodology, controlled experiments, theory building, and so on. Now, this pattern, as you know, during pandemic, how many of us have heard of hotspots? Hotspot pattern, right? It's a day-to-day language now. It has been used for many other things like cancer. They make maps, look for hotspot. If you see a cancer hotspot, they might do environmental investigation. Road accidents, they do hotspot. So it has become a more general methodology, and we'll show you other patterns. But broader question is in spatial data science. What are the other problems we can help you with? And you can imagine that during the recent pandemic, if you wanted to say what was the source of COVID-19. You can go look at the data in China, early days of Wuhan, and it's the seafood market. You kind of see the same hotspot patterns. All right, so that was many years ago, and you can ask, so what has changed since then, right? And what's the role of computer science? There was no computer science back then, at least as far as I know. So one big thing that has changed, which we all know, is big data, right? So we can collect a lot more data. It took John Snow several days to collect a few hundred cases, right? But today you can collect a lot more data. So this is sort of contemporary to John Snow. You are seeing Lewis and Clark expedition, right? And it took them several months to kind of survey part of the United States. But now we have sent satellites. You can scan the Earth. Last century, you could scan the Earth almost every other week, but today you have almost, a lot more nano satellites. You can scan the Earth every day now at meter resolution, fairly good. So a lot more data. Okay? And let me try to show you what you can do with this data, right? So there's a lot of this source, so these are your old satellites, $1 billion, looks like a truck or a bus. These are nano satellites, like a pizza box. In one rocket, you can send up hundreds of these. So there are companies with hundreds of these, and more are going up, right? So a lot more data. And not only that, this technology is becoming ubiquitous. So when we talked about Google Maps and so on, you probably know there are over 1 billion users. Okay? But GPS is used not only for location, it's also the clock. So most of our infrastructure, they are synchronized to GPS clocks. So lots and lots of this. And if you have GPS on your phone, you can collect data about people's location. Okay. But anyway, this may not be intuitive to many of us, but now GPS is as essential as electricity for our civilization. And people are developing ground-based alternative for it. But coming back to the data story, there is a lot of data. So remote sensing, I was mentioning, like these satellites, and this data is valuable. It's not just petabytes of data, but people are assessing its value for energy exploration, for many other things. And these are big numbers, right? I mean, we do have big companies in this town, right? Microsoft and Amazon. How does this compare with their annual revenue? What do people think? Is this bigger than their revenue or smaller than their revenue?
Bigger?
It's bigger, right? And that's why all these big companies are trying to come and get a slice of this space, right? So everybody's India. Another one, as I mentioned, smartphone and so on, we have GPS, right? And as you know, if you leave your location services on, then everybody on your phone, all the apps and Apple, and they're all collecting your locations, right? And they have been selling it for more than 10 years. And people, this is a 2012 report, and the value they estimated back then was again a big number, bigger than the revenues of Microsoft and so on. So again, very valuable data, and I will show you what people can do that. And this is just the beginning. There is more. If you are driving a car, all the cars sold in this century, they actually measure more than 100 variables about your car, energy, emission, and you can use that data. This is augmented to the GPS, and you can do things with it. Okay. Social media, if you are using Tweet and so on, about 5% of them have locations, right? So a whole lot more data that, probably not a surprise. You all heard about big data. But it allows you to do things that we could not do before. Okay, so I'll give you some illustration. So for example, looking at the crops worldwide, the agriculture. About 10 years ago, you had Arab Spring. Anyone remember Arab Spring? A lot of governments toppled. And it was because of food prices, right? Because we didn't have a good sense of what's happening around the world. So many food exporters, they stopped exporting the food, right? But after that experience, many countries came together and they said, we have the satellites, we can observe the crops. So we are going to look at that and publish a map every month. And this is very recent. This is just 2 weeks ago. Okay. And you can start to see this is not a good year. You all know about droughts in US, in Europe, but look at right here, see what's happening in Europe. Okay, the crops are not doing well. China, okay, even United States, the central part. This is a tough year, right? But now the interesting thing is you don't have to wait for the end of the season to know that we are going to have shortage of food, right? You can get this information months in advance and the governments can start planning around it, okay? So this is something every food company, every government monitors. There is an agreement across about 82 countries and they do this, right? So this is the power of what you can see from the satellites. And this is just the beginning. You can see water resources. Many of you know rivers are low, right? Navigation and all that is happening. So a whole lot more you can do. Let's do another one closer to, a project we have. So another space which was very hard to monitor before was ocean. As you know, in high seas, a lot of goofy things happen. And but about 10 years ago, people required large ships to report their location. Okay, this was initially to reduce collisions, but now the data gives you other patterns. This is called AIS data. And this is showing you the location of the ships, which the data that has been reported. And you can start to see other patterns of light. Okay, here is an interesting pattern. You see this ship is reporting location, reporting, stops reporting for 2 weeks. And this is Galapagos Island area, marine preserve, right? This is a fishing vessel. So what is your conjecture? What's maybe happening there? We don't have the ground truth, but what do you think is maybe happening there? Yeah.
Fishing.
Probably illegal fishing, right? But it's a conjecture, right? But the nice thing is if we flag that, then other civilian organizations can look at satellite imagery, right? Or they can send a drone over there, right? To verify. But there is a huge effort right now to protect these marine habitats, and this is a key data set to say where to focus, right? Because it's such a big area. And we have a project from NGA to look for other patterns like that. So let's come close to home. Those things may be a little bit remote to us. We all use Google Maps. And as I was telling you, these vehicles, they are giving you hundreds of variables about your energy use, your emission. Gas prices were relatively high in California. I don't know what were the gas prices in Seattle area last few, $6, or just like California. Okay, so how many of us would actually find it interesting to save gasoline while we are driving? Few of us, okay, good. So this data can be used to do that. And here are some of our experiments from last 10 years of work with National Science Foundation and the Department of Energy. This is showing you two paths in Ohio, this green path and blue path between 2 points. And you can kind of see there is a little bit of difference in travel time, but a lot of difference in the energy use. These are electric vehicles, hybrid electric vehicles. But same thing you can do with gasoline. So when you pick your route in Google Maps, you can actually say, don't try to minimize the distance or travel time, but try to minimize the energy use or emission, And this facility actually has come, Google Maps just introduced it. Looks like this is frozen. How many of us have seen eco routing on Google Maps? It puts a leaf. Okay, good. Last October, they started it. All right, I may need some technical help to move the slide forward. Still a bit frozen. Oh, there it is. Okay. Maybe use this. So essentially, now you can think of your navigation services as giving you more options. And as I was mentioning, this just got supported more broadly. But these kinds of things you are going to see more and more of. And this is based on this onboard diagnostic data. Okay. Here is another one related to the pandemic. So during pandemic, the governments were really struggling to see what kind of preventive actions to take and are people complying and, and things of that kind. So state of Minnesota had asked us to analyze this data. So this is essentially locations of smartphones in, safe graph aggregated it. This is about 5 to 6% of Minnesota population. And it is showing you the spatial spread. But they were looking for certain analysis. By the way, it's all privacy protected. It's very much census-like. So we are not looking at anybody's individual trajectory, but these are counts of cell phones in different areas and some statistics. But one of the things they were trying to do was number one, compliance. Are people actually staying at home during that time, or they are getting impatient and they are leaving, right? And that data you can see from here. And they will try to, as soon as they see people are impatient, they will try to take action. Safely reopening the economy. They were trying to figure out which business categories after stay at home you can open safely, right? And one of the risk factors there are these long visits. So, for COVID, you have to have face-to-face contact, right, within 6 feet for 10 minutes or so. So this data, you can actually try to see long visits. Where are people lingering? Because those are the places you have to take more precaution. And one interesting thing you see is difference between limited service restaurant and full service restaurant. The full service restaurant have a lot more long visits, right? The same thing you kind of see, lot more long visits, but limited service, not as much. So they could say, well, we can open up limited service restaurants very quickly. But for full service restaurant, they went and tried to think about other ideas, like block the parking lane and put benches outside, stuff like that. So anyway, this allows you to see lots of things which were hard to see before, okay? It's not only in geography. You can actually go down to microscopic scale and cellular scale as well. So this may look a little bit unusual. These are very, very new data sets that are coming out. And what we are showing you here are essentially biopsy slides. So if you have ever known for cancer and so on, they take a tissue sample, they put it between slides. Old days, you could only see 2 colors. So they could just do normal tissue and cancer. Now what you could do is like 20, 30, 40 colors. And so these dots are actually the cells. And they are telling you what kind. So there are some immune cells, B cell, T cell. They are going to fight the cancer, and this tumor or the red ones are the cancer. Okay. So if you see cancer, by one side and no immune cells inside, that's not good news, right? But even when the immune cells come in, they are patterns, because this cancer is very clever. It tries to fool the immune cells, saying, I'm not really a foreign cell, don't kill me. Okay. So you have to look at other patterns. So basically, we get tissue samples and these pictures from people who are responding to a particular therapy and people who are not responding to a particular therapy. And the hypothesis is that the spatial arrangement is something of interest. So they want to know what's the difference between the maps of these two, right? So in this data set, for example, it is saying these natural killer cells, whenever they are with the white blood cells, that can separate, the responder from non-responder, and so on. But anyway, this is something with Mayo Clinic, and this helps them test different therapies and so on. And the same spatial pattern is of interest, because for a T cell to kill a cancer cell, they have to touch. Okay, if they are far away, it's not as easy. Okay, so the message was we have a lot more data, and this data is of value. You can solve the problem you could solve before. You can see things you could not see before, right? So I want to pause here for a minute and just see if there are any quick questions on the data side of this space. Okay, probably not a surprise, right? All of you knew. The main thing to remember is that among all the big data sets, spatial is the biggest of the big data set. That's what a lot of people don't remember. If you go back to McKinsey report, everyone remembers about health or manufacturing, but you look at the value, the biggest value was on location traces. So that's something to remember. All right. So if you have this big data, it's not easy to process it on machines like this that all of you know living next to Amazon. So we have to use big machines, and because you have to download this data or analyze it, it takes time. So the good news is that cloud computing and spatial data have come together in very nice ways, and I will just send one or two messages here since you are neighbors of Amazon. So there are different platforms. So these are desktop platforms. The ArcGIS. This is the traditional one. Anyone who has used ArcGIS here? Geography folks. Okay, good. But now, if you want to go to supercomputer, there are a whole bunch of things going on supercomputer. So you can use that. Or if you want embedded systems, right? You want to take something portable on a UAV and collect and analyze GIS data. So the whole spectrum of architecture is becoming plausible. But more interestingly, let me actually mention, a simpler thing. This big data that's coming together is also becoming accessible because it's available on cloud. So I'll just show you a few examples. So here, how many of us know this AWS here? A lot of us. Okay, good. So they do host a lot of spatial data. Okay, Google Earth Engine is another one, and there are some government servers, and there are equivalent servers in other countries. So this is alphabet soup, but it's all it's telling you is there are a lot of big spatial data which is on the cloud. You don't have to download. You can just go there and do your analysis and get your result back. Okay. So to introduce this alphabet soup, let me actually ask. In this one, has anyone seen it? Are you familiar with any of this data set? Do you see anything familiar in this big list? Okay, which one do you see?
Sentinel.
Which one?
The Sentinel satellite.
Sentinel, yes.
Sentinel.
Sentinel, yeah, this one, right?
Yeah.
The European satellite, that's pretty high resolution, and a lot of people use it, and you can get it from here, right? OpenStreetMap, some of you may have heard about, right? Yeah, good. And for people in computer science, there is also a little bit of machine learning data. So there was a DARPA geospatial cloud. So they actually put out labeled data. So with satellite imagery, they say here is a building, here is a car, here is a truck. So you can run your CNN and train them and things of that kind. So labeled data is also coming. But key message is that you don't have, don't say that I don't have access to the data. So there is big data and it's accessible. That's the main message here. All right, so we will go next to the GeoAI part, and the way I define AI may surprise you a little bit, but feel free to object or debate and so on. Okay. So once you have the compute power, once you have the data, right, then people get more ambitious and say we want to make sense of the data, right? From data you go to information, and in our world, actually there is a term called intelligence, right? So when we talk about intelligence from national security perspective, it means a lot of different information which is actionable. And if you know the intelligence agencies, there are a dozen of them, and one of them is focused on what is called geo-intelligence, right? This has been there for a long time, and they collect maps of different kinds. Okay, this was born because of this picture from Cuban Missile Crisis. Anyone seen this picture or remembers Cuban Missile Crisis? What is this picture about?
I don't remember.
Okay, but do you remember Cuban Missile Crisis? Okay. So basically back then they used to fly airplanes and take pictures. And one of the airplanes, took this picture over Cuba. And what is interesting about it is that you see this configuration. This is called Star of David. So one triangle here and the other triangle here. And then you see these things arranged here. This was the design of Russian missile sites. Okay, so they had seen a lot of this in Russia. And suddenly they see one in Cuba. Okay, then you can guess what happens, right? What are they thinking? Right? Russians are building this here. So they fly more airplanes, they see a bunch of these there. Okay? And that's the beginning of geo-intelligence. They now saw the reason that they have to look around the world and look for what's happening. Okay. Now, so this was the situation back then. You had photographic films, these aircrafts will bring it, you develop it, and people are looking at it and figuring out what is this, right? How does it work today? So many of you probably knew that even before Ukraine war started, right? The intelligence agencies were saying, oh, it's coming, right? How did they know the war is coming? Right, you remember the news before the Ukraine war started, almost several weeks ahead, they were saying it's coming. How did they know that? Yeah.
Were their troops being mobilized or Ukraine?
Right, but how did US know the troops were being mobilized? The satellites, right? So they were watching, and what is happening with satellite imagery now that we can run some basic CNN, and it will not only get this image, but it will recognize it, right? It is saying, look, there are aircrafts there, right? There are aircrafts, how many aircrafts? And not only that, next to aircrafts, there are other things. There are people are there, right? Because you can have a whole bunch of aircrafts in a desert, right? Because that may be a graveyard for aircrafts, right? So you need to know there are aircrafts, there are soldiers, right? So they were looking at the patterns, and that was indicative of an offensive maneuver, right? So this is what is happening now. All this imagery comes in huge amount. They first go through some kind of a processing software. Computer science, we may call them AI, right? Or electrical engineering may call them image processing or whatever. But today, the life has moved. You are finding these objects, okay? And this technology is going around the world. People are so concerned about the security aspect of this technology that US tried to put export control on that. And this is a very simple technology. But let me tell you, how many of us have played with deep learning here? One, okay, few, all right. Let me show you what they are trying, they wanted to protect, and tell me how sophisticated it is. All right. So they are looking at geospatial imagery, not any arbitrary video, as well as LiDAR. And just 4 things. It says there is the software has a user interface to create training examples, right? Then it does some kind of augmentation or data cleaning, trains the CNN, and then it uses the trained software to process other imagery, right? You could use that as an undergraduate lab, right? Nothing very sophisticated. Why would they try to make a restriction saying you cannot export this software? I mean, every person can do that here. Because the societal implications are huge, right? Because satellites are, many countries have satellites. They can see all this thing. But in past, you had to hire thousands of people to scan them and know what the adversary is doing. With CNN, instead of 1,000, you can now just get away with a dozen people, right? So this is going to be, so all I'm telling you, once you marry these AI and fancy things with geospatial, suddenly your societal, importance and everything is at a different scale. Okay? So this is a fairly simple and well-developed knowledge, right? And people have been using different kind of AI and deep learning. So people who are new to deep learning, I just wanted to tell you in one slide why the excitement is about. So this one, eCognition, is the traditional remote sensing software. Anyone use eCognition or from remote sensing side here? Okay, yeah, don't worry about it. But basically, it was like a traditional computer vision, and it was successful in many other areas like Haiti, where after Haiti earthquake, people had left the city. And to locate them, people basically figured out that this blue color was an interesting feature because in those areas, blue dot was given out to the people who were away from city. But once you knew the feature, then you can run through your image processing software to plot them, right? So this is your traditional workflow. You do some cleaning of the data, but feature engineering, blue color is important, okay? And then you run through your machine learning and you do post-processing. But what deep learning is doing is to kind of reduce the need for feature engineering. It can do both of them, right? So it just makes the pipeline simpler. And there has been a lot of excitement last 10, 15 years on this, and people are using different things. So I'll just show you a little bit, for example, in images of urban areas, you can count vehicles very quickly. You can pick out where vehicles are. You can pick out where trucks are. You can pick out trees, houses, all kinds of things. Department of Energy is going to map every single house in the US for their own perspective and so on. So the mapping world is changing. Okay? We had other projects where we were actually trying to look for trees. So just with LiDAR data, the height and the aerial imagery, you could actually pick out the trees. You can do things of that kind. Of course, machine learning, deep learning, despite its success, it still gives you maybe 80–90% accuracy. If you're interested in going even further, 99% and so on, then you do have to go back to remote sensing and do a little bit cleaner. But huge growth on this one, and I will skip this. Okay. All right. So people have been doing this automation, and you can ask, is that the end of the world? AI has it solved all the problems, right? That's often what media tells you, that AI will do everything for you, right? But there is more to life than that, and I will go there. But before I go there, are there any other quick questions on either the hardware platform or basic processing? Yeah.
Is there any advantage to having like LiDAR sensors on the ground, say like on a car? I can tell you more information than LiDAR in the air.
Yeah. People have used LiDAR on the ground vehicles quite a bit. So in Iraq war and so on, because you wanted to see inside the buildings, and satellites cannot easily see that. But if you're driving a vehicle, you can see through the glass and stuff like that. Yeah, so LiDAR is used on ground as well, even self-driving cars. The better ones, not Tesla. Tesla is too cheap to have LiDAR, but you get the cars have LiDAR, because when you have bad weather, your vision is useless, right? If you have snowstorm, rainstorm, dust storm, computer vision is useless, and that's what Tesla loves. But better cars actually have LiDARs, because they can see and they can still avoid obstacles. Right? So these are good sensors. Any other questions? Okay, so let's say what happens after the geo-intelligence. Okay, we got the imagery, we process them, we know how many objects are there and so on. But really, the reason that we use the word intelligence is after all that processing, you still need to make sense. So this is the life of a geospatial analyst or anybody working on high level of corporate or large organization. They have to put this new information in context. As I was telling you, I can have 100 aircraft, but if there are no soldiers nearby, there's nothing else, it may be a graveyard. Right? But if you have certain other configuration, then is it offensive or defensive maneuver. And that's what these analysts do, and there are thousands of them watching different areas. So for them, after AI, after you have done object detection, you need to find patterns or patterns of life. Okay, that's where I'm going to go there. Okay. So, and this is an illustration of that. Okay, all the fancy computer vision, you can run it on this particular image, right? So first of all, when you see this image, what do you see? As a human, when you look at this picture, what jumps out at you? Yeah, and anything interesting about the president? He's pulling a prank. He has a sense of humor, right? What do you think CNN sees in this picture? I mean, CNN can see there are two presidents, one over here and one over there. Oh, right? But it's not going to say there's a sense of humor here, right? And that's why it's not enough to run AI and CNN, and those are first level things. You still need to go beyond that and do pattern mining. Okay, and humans are much better at that, right? Yeah. So all I'm saying is AI can learn a lot from other places, and it is happening. You see a lot of government agencies which are having these new projects. Just the LiDAR is one example. You talk to computer vision people, they are so obsessed with the visual map, right? And they don't think of other sensors, which many of other people use. And there are a whole bunch of these, things. And in fact, we had the IR person come and give a talk at the conference. He talked about this smart, and he had other, another project that just started on Haystack and so on. So people realize that. But AI is a big area. You see deep learning here, machine learning, but there are many other things. So I just want going to go to AI for a minute and say how AI can learn from this space. So going back to the LiDAR, this is an actual, case study. When the self-driving vehicle were in Las Vegas, they were trying to do demo and it started raining. And you notice that none of them could drive. Okay, not only Tesla, but even more fancy like Google Waymo, none of could do very well because their sensor suits are limited. They have visual sensor, they have a little bit of LiDAR, but you can actually do other sensing like thermal and so on. So let me take you to remote sensing world. I actually already asked how many of you are from remote sensing. But if you think from remote sensing perspective, this is what computer vision is focused on, visual map, very tiny, okay? But you all know that, there are other things like infrared, right? You see that in spy movie. There are things like microwave, right? When you heat right? And all of these things can be used for sensing. When you are sensing ice sheet on the poles, visual band is pretty useless. You have to go to microwave, okay? And so on. And all of this has been done in remote sensing for many, many years. And it's time for computer vision people to expand their horizon and do things better to save lives and so on. Right? So all it is saying is, you can do different things. AI is not end all and so on. Even in our conference, one of the speakers was saying, all the students nowadays, the only thing they want to learn is AI. And they have a tough time telling them that's not good enough. You need to know domain knowledge to solve real problems. And I'm going to, enforce that message. Here is another great popular AI. Google, does all the searching, right? And suppose I ask Google a very simple question right here: distance from Washington DC to USA, right? So first of all, geography. Geography. If I ask you how far is Washington DC from United States, what will be your answer as a somebody who understands space? 0, right? It's inside Washington. What will Google answer here? Any guess?
From Central US.
Google only understands points, right? So Google is putting USA as a point, Washington DC as a point, and it's saying, oh, it's thousands of miles away, right? Because it doesn't know anything better. So text processing and NLP, which is very fancy, right? They are doing GPT-3 and all kinds of claims. They can't answer a simple spatial question, right? So again, coming to the spatial world, you all know basic geometry from high school. Yes, points are great. Google started here, that's great. But we all know there are line strings and polygons. And this has been standardized 25 years ago, right? Juan Perlin, her course teaches you that. And there are libraries which also have all these operations. So this not in distance you can do with polygon and point. You have all kinds of topological operations. These libraries are available. How many of us have used any of this type? Spatial library here, OGC simple picture types, couple of us, wonderful. And this is basically available to all of you. It's in Python, in Java, in SQL. If you are working with spatial data, don't think like Google. Go beyond points. Life is more than points. Okay? So this is what we teach in spatial database. And then there are patterns, right? So once you have detected the aircrafts and soldiers and so on, then we look for these kind of patterns. So hotspot we already talked about, but I'm going to talk about a few more patterns. And this is where we are going to data science now, right? We often talk about these patterns. So in our world, so again, quick show of hand, how many of us know data mining here, the vocabulary of data mining? Few of us? Okay, good. So data mining thinks in terms of these patterns, and you put 3 adjectives in front. These patterns are useful to some domains, it's applied field. They are interesting means they give you new information, which was not previously known, and they are non-trivial in the sense there are many, many candidate patterns. So you need an algorithm to sort through it, right? So if you're testing one hypothesis, that's not data mining, you go to statistics, okay? But I'll show you some example of that. And then there are different pattern families. In the regular data mining, your pattern families are like association rule and other things. But when you come to space, the pattern families are different. So I'm going to explain a couple of these and try to move towards the end of the talk. So hotspot we already saw before, London power up. And now there are software like SAT-SCAN. If you run it, it will give you this circle and it will tell you it's statistically significant. I don't know if you can read this here, but it can also tell you it's not a chance cluster. It can do some guardrails, because this is another difference in our space versus typical AI. A typical machine learning AI is used for very low stakes games. What advertisement to show on which page. If you make a mistake, what's the cost? Almost negligible, nothing, right? But when I'm detecting hotspots and I label a neighborhood as a hotspot in error, what is the cost? People stop going there. You saw that last 2 years, what was happening, right? Economy tanks and the politicians lose elections. So if you make mistakes there, stakes are much higher. So you have to have more safeguards. And that's why one size fits all machine learning or AI, if you bring and use it here, you have to be very careful. So people have developed new things. Okay. This is sort of the other pattern, co-location. We'll talk about it. And then cancer and immune cells are separate, then your prognosis is very different. If they're interacting in a certain way, your prognosis is different. So these are other patterns. So let's actually go. And the main point, as I made, there are many challenges here because of which traditional data mining or machine learning is not appropriate. And I'm going to show you a little bit of each and how new techniques can do better. So I'll start with a very simple thing like finding hotspots. So people who are taking data mining, if I were to ask you to say, how would you find hotspot? What technique will data mining recommend to you? And if anyone does their dense area detection, anyone has looked at techniques for that? DB scan, anyone? Okay, let's not then worry about it. But there are techniques, and I will just show you what they do. So this is from traditional data mining. This very popular technique is called DB scan. Okay? But the problem is they are easily fooled by noise. If I throw DB scan on this, it will still find a bunch of dense areas, but it does not check for statistical significance. This could happen just by chance. If you are throwing darts at a board, once in a while, some darts will be together. Okay? So it gets fooled easily. Here is, this is the signal test, and that's the background noise. And you see DB scan getting fooled all over the place. This is one of the most popular hotspot detection in data mining. But for us, since our cost of errors is high, we have to do extra work. And we basically add statistical significance testing. And now you can see you can clear out the noise and do the signal pattern. Okay. So additional tests have to be done in our space, and that's the main message here. Let me give you another challenge, which people in geography know about it for a very long time, and I wish other communities will pick it up. And so let me first illustrate what that is. Okay. So now we are going to this correlation kinds of patterns. So suppose I have this data. There are red dots, blue dots, and yellow dots. And people are asking which color of dots are together in space. So whenever I see one color, I see the other color next door. Okay. If I were to pose this question in using traditional methods, you will use association rule in data mining or possibly Pearson correlation coefficient. But in this situation, you will have to discretize the data. So you'll have to cut up this space into units like zip codes or and things like that. So if I cut up the space this way, right, then you have 4 different areas, and you can make vectors. So red vector will be 1 here, 0 in these 2 places. Okay. Blue vector will be 1, 1, 0, 0, and yellow vector will be 1, 1, 0, 0, right? And you can then try to see which vectors are similar, right? So you can try to compute Pearson correlation coefficient, and you will see red and blue are similar, but yellow is not. Okay, so these are your numbers. Okay. But notice that this is very unstable, because if I change the partitioning, right? You can imagine if I change the partitioning, the numbers will flip. See, if I change the partitioning, the numbers change. Okay. So many traditional statistics or data mining methods are unstable in this world, right? This is folks in geography, what is called formally. Have you come across this kind of a problem? Wonderful. So that's the technical name. In day-to-day life, you may have come across another phenomena. Since election is going on right now, do you see some games in elections where they try to change the result by changing partitioning? What is it called in real life? Gerrymandering. Okay? The thing to realize is gerrymandering is not unique to election. It applies to lots and lots of statistics and data mining, and very few of us realize that. Okay, so that's the key message here. Now, people have studied this for a long time. To get around the gerrymandering, what they did was to say, don't partition. So let's compute the statistics on what is called a neighbor graph. So instead of partitioning, you connect these points using some neighbor relationship. For example, simplest is based on distance. And you can again say, yeah, but your distance that you choose will matter. But distance is much easier to handle than partitioning. It's a single scalar. And you can define the functions to be a function of distance. So once you define a neighborhood graph, then you can compute the statistics on the graph. So just counting the edges and the rows. And these are, I would say, much more stable than the partitioning based method. And this is the crux of spatial statistics if you're new to that. And of course, these functions, these are not, the value is not just a number, but these are functions of distance that is used to define the thing. All right, so this is, I'm going to skip a couple of slides to manage time. And let me kind of go to, so yeah, I will go to one more main point and then we'll try to wrap up. The third challenge in this world is what we call spatial autocorrelation, which is being realized by many, many communities. So if you're coming from traditional statistics, and how many of us know linear regression here? Quite a few, good. So you probably know that linear regression has this assumption, IID assumption. How many of us know the IID assumption here? Okay, what does IID stand for? It assumes that data samples are drawn independently of each other and from identical distribution. It may work in other domains, but doesn't work in geographic data. And I'm just trying to persuade you visually. So here is a map where each pixel property is drawn independently of the property of all other pixels. And look, this looks like white noise. How many of us have seen maps like this? Okay, you have seen, okay. But more maps are like this, right? Where nearby things are similar. And that's the first law of geography. So if you still use linear regression and other methods like decision trees, which are treating each pixel separately, you are likely to not get as good a result. So this has been slowly realized, and there are many methods to handle it, and I will just show you this one table. So linear regression has been generalized to what is called spatial autoregression, where they add a term to look at neighborhood values for the prediction. In other methods also they have done that, but let me just highlight one more. So in neural networks, right, we talked about CNN, right? How many of us know CNN? Many. And you realize that's what it is doing. It's modeling autocorrelation. To classify a pixel, it looks at nearby pixel. They call it convolution, right? So there are many ways to call it Markov random field or convolution or spatial autocorrelation. But this is one way we start to differ. And we'll give you one more. The second issue is the second eye. The second eye is everything is drawn from identical distribution, right? So you assume that your whole population is homogeneous. And again, that's a problem with spatial world. So you probably can see that even in simple things. So you look at here farms in Midwest, right, where I come from. Here are farms in India or China, and you can see how different they are, right? If this kind of a farm, you can classify crop health using a very coarse imagery, right? Very simple machine learning will work. But if you're dealing with these in China or India, you have to have more sophisticated sensor and a different kind of machine learning. So this is called the heterogeneity. You don't want to fit one model and hope that it works everywhere in the world. You want to fit different model to different parts of the world, right? This may go against our general grain. In computer science, we love general models. Space, you have to think differently. That can only take you so far, and you have to customize the location. So again, GWR, any of us talked about graphical weighted regression. So just give you one way to think about heterogeneity. So here what we do is to leave the linear regression as it is, but these coefficients in linear regression, instead of being scalar, this is not a scalar anymore, it's a map. This is not a scalar anymore, it's a map. So you basically, your model, even the weights of different factors, they vary from place to place. And this is a model which is well implemented. And you can, kind of see some new work. So I will show you that. So in CNN, for example, it's still, in CNN, the weights are all scalar, right? Each weight has same value everywhere on the world. But a new thesis in our group, we are saying the weights are not a scalar, they are maps. Okay, so this is called spatial variability aware neural networks. And that can improve the performance of these things when you go to larger problems. Okay, so we'll try to kind of bring it back to simpler things. But spatial data science, you kind of see, it's mixture of statistics or more mathematically rigorous techniques to understand the limitations of traditional data science for spatial data and make them more powerful. And these methods are not really specific. They are actually more general than old methods. If you set autocorrelation to be 0, you will go back to old methods. Okay, if you make those maps to be single location maps in GWR, you will go back to the lower thing. So these are more powerful methods. The last thing I will just go to is visualization, and then we'll close and do the question. And many of you have probably seen that. So how many of us have seen this Google Earth time lapse visualization? Has anyone seen this? Few of us, okay, good. So let me actually play this CTAC one, because there is so much satellite imagery that now you can think of these as video instead of thinking at static maps. Okay, see how do I close this out? Do you know how to close this microphone? Okay. So this is showing you about last 30-40 years in Seattle airport area, right? So each year they took the satellite imagery, they stitched it, made the video, and this is covering the whole world, right? So in your own neighborhood, you can try to see what changed in last 30-40 years, right? So because now so this is just the beginning. This took a lot of effort for CMU and Google to do that, but now this is one snapshot per year, just 40 frames stitched as a video worldwide, right? So imagine Google Maps or Google Earth as a video. And now this you can do for daily Earth scan, and you can see the details. In fact, the big IARPA project that I was mentioning before, they are viewing this as a satellite video, and they are trying to find all the areas where construction is happening and determine the construction stage. So those are the level of analysis that can be done, and you can kind of see some of that happening over here. So I think that was the last part I wanted to make. Let me go back to PowerPoint here. Yeah. And I'll try to close. So we are fortunate our data can be visualized with space and time. So I showed you the satellite. And there are other things like crime around, during the different hours of the day and 3D visualization. But last thing I just wanted to mention that, many data science degrees and curriculums are coming around. And they are not always paying enough attention to spatial, despite its societal importance and growth. And this is sort of a big, a call from University Consortium on GIS. And it's basically saying in data science degrees and curriculums, you should bring some geography content because there is a lot of data, right? And these data are very valuable, as I was showing you. And they present unique challenges. You can't just take, one size fit all AI or machine learning and start working with it. You need to learn some new techniques. I talked about a few of those things like autocorrelation. If you remember autocorrelation at the end of this talk, the talk has done its job. Okay. And then make sure you don't use IID things on here, but there are other things like geographic variability and many other things. So there are new techniques, there are different ones, and some of us, our geography friend, we're sharing a few of them. So whatever courses are around, it's good to have some exposure of this. Right? So this is essentially a call to action to make sure data science majors and so on, they look at it. So again, all of us use Google Maps and Uber and food delivery, right? I mean, it has revolutionized our life already, but many more compelling opportunities are ahead because you are getting new data, new applications. And so the ask is all of us to at least think that spatial is not yet another application, but it has some unique properties and unique techniques, and you should learn about it. So with this, I'll stop, close the talk and see if there are any questions and so on.
Yeah, please raise your hand if you have any questions for Dr. Shekhar.
Okay, maybe go from there.
So, thank you. So, I was going to post convolution and you can go to images or secondary images. So, I want to ask, like, why did you not start with using one mean square PS and everything? PS and basically checking out the dimensions like image
Right. No, I was not using CNN to improve the noise. So all that is done in pre-processing. So when satellite imagery comes in, NASA and others, they will take out the cloud, the atmospheric dust. All that is done. But CNN is used for object detection. So you want to say, count all the houses in Seattle or count all the airplanes next to Ukraine. Right? That's what CNN is used for. In old image processing, they used to have some filters. But they had to build each filter for each type of object. So for house, you have this filter and you go around doing that, right? For aircraft, you have this filter, you go around doing that. But imagine how many types of objects are there. So CNN, the beauty is that you don't have to design the filter. You just show some examples to CNN, variations of CNN. It will learn the filter for you. And then it will go and check rest of the image. So that's the excitement of deep learning. Yeah. Yeah. So ResNet is a variation of CNN. The actual ones I should say is YOLO and ResNet, but there's so much alphabet soup for a broad audience there. So CNN is a good start.
Thank you.
Yeah. Okay.
Do you think that transformers have a future within spatial design?
Very, very good questions. So transformer, if I say it in spatial language, is basically saying teleconnections. Okay. So autocorrelation says nearby things are similar, right? And that's the first law of geography. But once you go past that, there are teleconnections in geography as well. For example, how many of us know El Nino here? La Nina, right? Which this is a La Nina year, right? And the reason we are interested is because that thing over Pacific near South America can affect our weather. And that's an example of teleconnection, right? So whenever you have flows, then you have these long distance interactions. So even the spatial autoregression model that I was showing you, remember the W matrix that I was showing? So W matrix essentially allows the relationship between any location and any other location, right? It's a full, right? If you have million location, it's million by million. So it is able to represent both local relationship and long distance relationship. And there was literature on learning W from the data, which is more powerful than transformers, right? So transformer is a way for this community, natural language community, has finally rediscovered teleconnection. Just like CNN rediscovered spatial autocorrelation from biology, they could have learned it from geography much earlier, you know. So yes, yeah, transformer is an idea which is very much studied in this space, and people look for teleconnection. If those things can scale up to our scale of data, then it will be nice to see whether our W learning methods and transformers do they compare. Yeah, the same idea. Yes, go ahead.
Yeah, so you said, order to have a like general model integrated to, look at receiving data from, different parts of the world, like setting up, but what about the fact that it's like a farm, it's a route,
Yes, yeah. So there is so many things I'm talking about in space, they are not unique to space. They happen in time, they happen in physical world. Just that spatial people were early in talking about it, right? So there's a huge variation in time, it's called non-stationarity, right? And people also think about that. So time, there are some cycles which are very well known, particularly for human life. You have a seasonal cycle, right? You have a weekly cycle, you have a day and night cycle. And many cases, people actually separate these. So if you're thinking about traffic in Seattle, right? So your rush hour traffic behavior is different than non-rush hour. And people will segment it that way. So people will also say, but with the periodicity, you can kind of do that. But yeah, exactly same ideas are applied here. Okay? But temporal methods haven't adopted as much. So I don't know, do you do time series analysis, signal processing? Do you know ARIMA models and things like that? Not as much. See, autocorrelation has percolated around all the domains. Okay, so time series people do a lot of autocorrelation, ARIMA. But the variability is not as well studied. So this will be a good place to try to see if I take these ideas like GeoAI over time series, what would they look like, right? And in general, spatiotemporal, you have to have both. Yeah. It's a lot of open space. Any other questions? Yes.
Why not just use low-tech camouflage
Okay. For
in terms of like satellite images to hide your planes?
or to fool them. Oh, perfect. Now you are telling us why AI is not enough. And it's done all the time. Russia, I can show you the images of those.
Okay.
And it's done in two different ways. So they would actually put these inflatable airplanes, right? So your CNN or analyst has to be clever enough to separate that. But fortunately for us, we have more than visual signature. So computer vision is easily fooled, but infrared, right? I mean, you can start to see temperature and all that, then you can start to separate, right? There are also fake maps. So Russia has been known to take image from here, put it over there, and release it to the news. And so a lot of those games are going. Yeah, but in the intelligence game, it's a cat and mouse thing, right? So there is no end to AI. And people think about how to fool the other space. So yeah, go ahead.
I was looking at the time lapse video that you showed. Anyone trying to use this type of math to find out which part of the system is going to grow the market, housing market after and here, the price of it here it's a little.
Right. So are there any urban planning people here, if I may ask? Any urban planners here? Okay. So this is an exciting possibility, but right now I don't believe urban planners are leveraging this data as much as they should. They mostly use an economic model, right? So they try to project the land rent and price, how they will grow. So their models are much more abstract, but they can use a lot more of spatial data.
So they combine maybe the present market prices, with those satellite images and come up with some.
That will give you some additional information, but there are still many other challenges that, like non-stationarity. It's hard to predict recession, right? It's hard to predict, right? Amazon at Q2, we didn't know where it will go, but wherever it went, probably they have it go. So they have their own challenges, they may have their own reasons, but they can use this data. What they have been using it for is a little bit different, mostly to understand which areas are, suffering. So from satellite, you can see these are the areas where you don't have good infrastructure or drinking water. So then you can concentrate your aid and develop those ideas, those kinds of things. Yeah.
This may be far too general of a question, but you talk mostly about like geography of the Earth, right? Is this did not have any application of like space looking for life or potentially analyzing like non-asteroid dangers or something like that?
So I don't know that far, but the technology when you look outwards on the stars is a similar technology like Google Sky. So it's, you know, the sky catalogs, they take all the imagery, right? And initially what they are doing is to find objects like stars and galaxies and things of that kind. So it's a very sort of flip problem. So just like instead of house and truck, you're finding stars and galaxies. So they do a very similar kind of technology. But one big difference is the coordinate system. So when you're looking at the Earth, you talked about latitude, longitude, which I don't know if you realize they are angles really, right? Latitude, longitude is an angular thing. But most of us don't think about it that way, right? We said X, Y coordinate is latitude, longitude, right? But when you're looking outside, it's all angles. So when you pose a query, when you analyze, it's all angular. Whereas when you're looking down on Earth in small area, we often try to go towards Cartesian coordinates. But bigger area, you will do spherical. So there are some differences, but the systems are very similar. Postgres, I was talking about, they use Postgres. Great.
So you talked a little bit about how there's a different level of risk when it comes to, for example, using spatial AI in ad services versus in healthcare. And so I'm more interested in healthcare. Is usually the risk more of predicting, for example, predicting too much or not being able to predict something dangerous.
Okay. So let me again ask, are there people in healthcare or setting here that they can tell? Okay. But there are two types of errors, right? Type 1 error and type 2 error. So you can miss some patterns or you can have spurious pattern. Now the cost of each depends on the domain. Okay, the cost depends on the domain. So in healthcare, you have to ask yourself what that is, right? Like COVID-19 testing. Right, we do the test, they are easily available, we know they're not that reliable. So if you actually have a false diagnosis, you know the cost, right? And after a few days you will know. You may stay home for a day, but you will know, right? If you miss a diagnosis, you will also know, right? After a few days, you might get the symptoms, right? So depending on the situation, you have to know what is the cost of type 1 error or type 2 error. The things I was bringing up are hotspots of accidents, hotspots of disease, infectious disease. Right? Over there, spurious patterns are more expensive. You said this neighborhood is a hotspot, people stop going there. So you want to put a lot of guardrails, you check statistical significance, you do many things. Okay? But missed pattern, you have to think about what is the cost. Maybe missed patterns are not as costly because after a few days, things will grow and you will get another shot at it, right? So it's only a delay, right? But depends on the disease. If it is extremely dangerous disease and you want to reduce the delay. So the type 1, type 2 error costs are very specific to situation and based on what they are, you need to different guardrails. Yeah.
So just I'm project right now.
Okay.
So you showed us there's a catalog of the traditional
Okay.
So one of them, the technical part is the selection part.
Feature selection.
Yeah. So that one was like exactly the one, or this one that one use the accuracy of the outcome, or you just
No. Actually, that's a very key point. That's the reason deep learning everybody is excited about. So let me go back to that slide. How many are from computer vision here? Not many, but I will tell you, this is a very interesting intuition without too much deep learning. Yeah, this slide. Yeah, this is what you have to understand. That's the main advantage of deep learning. There is not major magic in deep learning, but what is happening in the old workflow, you had 4 stages. Okay, remember each of these stages is a probabilistic statistical method. So each stage you will have 10% error roughly. Okay. But if you have 4 stages with 10% error, it will add up. Now you have 30-40% error. You see, if you reduce a stage, now there are only 3 stages, each with 10% error. Okay, you see. So now I have 3 of them. So instead of getting 30 to 40% error, you're getting 20 to 30% error. Okay. So deep learning, the reason that it reduces the steps in the pragmatic sense, that is its biggest power. Okay, that is its biggest power. Because now, because of that, your workflow is less and your errors are less. Yeah. Yes, go ahead. Right. Yeah. Okay, let me go back to that slide so you will know. Yeah, 1 second. So I think you're talking about this one, right? So this is the slide you're saying. You want to rephrase your question. So this is the traditional neural network. Here, every weight is a scalar, right? And this is the spatial variability aware, where the weights are not scalar. They may have multiple values, 1 value per location. Right? So you want to rephrase your question. See, another way to think about it is following. Okay, I'll just simplify it. Another way to say this is the following. You say you build 1 neural network for China, okay, 1 neural network for Midwest, 1 neural network for India. Okay, if you did that, then even though your architecture is same, the weights for the one common edge will be different in China, India, and US, right? So that's a simple way to view what I'm saying. But instead of India, China, you may want to think if you're doing agriculture, there are zones, right? So there are maybe 10 or 12 zones. So each zone train a separate neural network. Don't train a single one across all zones. That's a simple way to think about what I'm saying. Yeah, make it location specific because you will get more power. Okay. Or other words, in engineering, it's called calibration. Okay, if you look at engineering models, they would have one generic form of model, or in this case, a neural network architecture. Okay, but any place they go to, they will calibrate. Okay, if you buy a car, right? Since Seattle is mountainous, right? You have a lot of rainfall. Your engine calibration in Seattle will be different than the engine calibration in Phoenix. And that's sort of what is being said here. So it's okay to have same architecture, but calibrate it to the location because there's so much variability across location. That's the one more.
How much of concern is there about p-value hacking? Because you're running lots of these nets and all this different data. Eventually, something that's not significant is going to pop up as statistically significant.
Yeah. This is something missed by data mining people left and right, right? And machine learning people. So first of all, let me rephrase what he's bringing up. This is a major blind spot in computer science. Okay, statisticians know that. So can you give the formal name? Is it called multiple testing?
I'm not familiar with the formal name of it.
Okay. So let me explain what he's saying. So how many of us know p-value? P-value, many of us. Okay, good. So p-value, suppose you set a threshold of 95% confidence, right? What it means is that 5% chance we will get a false result, right? If you are testing one hypothesis, it's no problem. Okay, 5% chance of error, I can live with that. Okay. But if you are testing 100 hypotheses, what's the situation now? 5 of those hypotheses will test incorrectly, right? And data mining, that's the problem. We are looking at millions of candidate patterns, right? Like hotspot in SAT scan is looking at many of them. So if you don't pay attention and just do p-value testing, you will get a lot of spurious pattern because of the combinatorics. And this is a major blind spot in our area. Okay, very few people are looking at it. But at least I can tell you, our group, there is one thesis just exploring that, reducing false discovery rate. And if you're interested, I can connect you. Another person who is looking at it is in Boston, a smaller college in Boston. And so machine learning data mining, this has just started. And this is another place we can learn a lot from statistics, folks. So what is your major, if I may ask, what's your background?
Master's in computer science.
Oh, good. So where did you learn this amount of statistics?
Well, this is the things I learned in chemistry. I have a chemistry undergrad.
Oh, wow. I see. Very interesting. I didn't know chemistry was, of course, they use so much statistics. Yeah, now we can learn a lot from this. So we call it false discovery rate reduction, right, which is becoming important when you have such a big combinatorics. Any other thoughts? Great, thank you.
Thank you.